Welcome back, everybody. Part 3 of Section 5.2, Solving Trig Equations. We're going to wrap this sucker up today. A few more types of trig equations we're going to solve. Here we go. Alright, I'm going to say problem 5 is a factoring example. I'll explain why in a second. Find all solutions on the interval 0 to 2 pi, so same thing we've been doing. And notice with the equation I have to solve, something different's going on. I've got both a cosine function and a cosecant function in the same equation. Okay, multiple trig functions in one equation. We haven't seen that before. It's always been all cosines or all cosecants. So the reason I know this is a factoring problem is I have multiple trig functions that I can't combine together. Okay, I can't put this cosine and cosecant together. What I can do is I can split them apart through factoring and then deal with each of the parts individually, which we'll show you how to do in a minute. Okay, so that's how I know I'm factoring. Now for factoring to work, I need to get things set equal to 0. I need to get everything on one side of the equation. So I'm going to start by subtracting 2 cosine x from both sides. Oops, missed my C. There we go. That's going to cancel the cosine x's out on the right. So we'll say equals 0 on the right. And then on the left, again, I can't combine the cosines and the cosecant, so all I can do for now is rewrite it as cosine x times cosecant x minus 2 cosine x. Okay, so like I said, to get the cosine and the cosecant separated, I need to factor these. Notice both these terms have a cosine in them, so I can factor that out. I can rewrite this as cosine x times the quantity of cosecant x minus 2 is equal to 0. Okay, because if I distributed back, cosine times cosecant would give me the cosine cosecant. Cosine times negative 2 would give me that negative 2 cosine x. And the whole reason we factor is so that we can deal with each factor individually. The next thing I'm going to do is use the zero product property and say I can turn this bigger equation into two smaller equations. I want to solve cosine x equals 0 and cosecant x minus 2 equals 0. And the solutions to each of these equations individually will give me a solution to this larger equation that contains both of them. Okay, because if I can make this first factor 0, the whole thing will be 0. 0 times anything, 0. Same thing with the second factor. If I can make this 0, the whole thing will be 0. That's our zero product property. Okay, so let's solve these both individually. So I'm down to now two kind of simpler problems. Where do I want to do this? We'll do the cosine x equals 0 first, and we'll just take care of this right here. Okay, since we're talking equals 0, I'm going to go to a graph of the cosine wave. Cosine is the one that starts up at 1, comes down to 0, then comes back up. It does one cycle within 2 pi units. Okay, the halfway point would be pi. So my zeros would be at pi over 2 and 3 pi over 2. Okay, so those are the x values that make cosine x equal to 0. 3 pi over 2 and pi over 2. Okay, we'll save those there for now. Let's deal with that cosecant x equals 2 next. Sorry, cosecant x minus 2 equals 0. I was getting ahead of myself. Add 2 to both sides of this equation. We've got cosecant x is equal to positive 2. Now it's going to be helpful to think of that 2 as a 2 over 1 as far as a hypotenuse and an opposite side. Okay, let's go to our angles in standard position. We want to know where cosecant's positive. Okay, well that's going to be where there's a positive opposite side, so that will be in the first quadrant. And the second quadrant. Because again, both of these reference triangles would have positive opposite sides. Alright, so I've got hypotenuse 2 over opposite 1. Okay, 2, 1 looks like we've got a root 3, in other words, 30 degrees here. And same thing here, 1, 2, root 3. 30 is our reference angle, meaning that angle in standard position would be 180 minus 30, so 150 degrees. Okay, let's put all that together as we run out of room here. So my solutions then are x is equal to the pi over 2, the 3 pi over 2, okay, the 30 degrees, which is the same thing as pi over 6 if we convert. Hopefully that's one you're starting to memorize now. And then if I'm 30 short of pi, in other words, pi over 6 short of pi, I get a 5 pi over 6. All right, so there's all my solutions on the interval 0 to 2 pi. As far as how many solutions are we going to have, as we go through these factoring ones the rest of the way here, you'll see some where there's maybe one, could be more than this. All depends on what the equation is. All right, that's an example of factoring. Part B is the same idea. Why don't you take a minute, pause the video, run through part B, and then hit play to check your answer or play to get some help with it. All right, part B, another factoring problem, and I know that because there's both a sine and a tangent function in the same equation. So let's get everything on the same side of the equation then. So I'm going to rewrite this as sine x times tangent x minus sine x equals 0. Okay, I'm going to factor the sine out, which will leave me with a sine x times tangent x minus 1 equals 0. Okay, let's set each of these factors equal to 0. Okay, for the sine x equals 0, let's go to our graph of the wave, graph of the sine wave. And with these factoring problems, a lot of times you'll end up with multiple ways to solve things. Okay, you'll end up with kind of graphing and an angle in standard position. Okay, sine goes like this, between 1 and negative 1. Okay, the cycle ends at 2 pi. Halfway between is pi. And I also have a 0 right away at 0 here. Now, as far as which of those am I going to use, notice the way we gave this to you, and it's always going to be the same. We're not going to try to mix it up and trick you. But I'm going to say we are greater than or equal to 0, so including 0, strictly less than 2 pi. Okay, I'm not going to include both those because basically angles in standard position, 0, 2 pi mean the same thing. So I am going to use the 0, I am going to use the pi. I'm going to say I'm not going to include that 2 pi in my solution just because of the way I gave this to you. Now again, I could give it to you with or equal to 2 pi, strictly greater than 0, but this will be the way we keep it. Okay, next up, let's do the tangent x minus 1 equals 0. So tangent x is equal to a positive 1. I suppose there's two ways we could do this one. We can go to angles in standard position. Thinking about this tangent x as 1 over 1. Okay, where is tangent going to be positive? Well, that'll be in the first quadrant, where I'd have a positive opposite side of 1, positive adjacent side of 1, hypotenuse of root, root 2, sorry, and a reference angle of 45 degrees. Okay, then where else is tangent going to be positive? Well, it'll actually also be positive in the third quadrant, remember, because here I'll have a negative opposite, a negative adjacent. Okay, negative over negative makes me a positive. Two wrongs make a right, with a reference angle of 45 degrees here as well. Okay, and for this part, we end up with x equals 45, in other words, pi over 4. If I convert, and then also 45 past pi, in other words, pi over 4 past pi, so we could say a 5 pi over 4. Okay, I guess, like I said, multiple ways we could solve this one. I guess I'd recommend this for the tangent when it's equal to a 1, but I could also graph a wave of the tangent function We'll review this just because you got to be familiar with this for the homework as well. Okay, where does it hit 1 at? Well, it hits 1 halfway between its asymptote at pi over 2 and 0, which is a pi over 4. So that's the same pi over 4 we got here. And then probably the tricky part with doing this one this way is you've got to do a second cycle to get all the way to 2 pi. That second cycle ends at 3 pi over 2. Middle point would be pi. Okay, and that point at 1 halfway between the two of those would be 5 pi over 4. I don't have that memorized. I just know the answer from here. It'd be the same thing. Okay, so either way we get the answers. We've got x is equal to 0, pi, the pi over 4, and the 5 pi over 4. Okay, those are all my solutions to that equation from 0 to 2 pi. All right, last thing we're going to look at in this section is factoring trigonometric trinomials. Okay, oh boy, what do I mean by trinomial? I mean a trig expression with 3 terms to it. So 1, 2, 3, that's where the trinomial is coming from. And I can't combine these terms because I have a cosine squared, a regular cosine, and a no cosine. And hopefully when you see this, it's looking kind of like a familiar pattern to it. I'm going to say this is going to factor the same as 2x squared plus 3x plus 1 equals 0. Okay, notice if I replace the cosines with just an x, I've got basically equivalent expressions. Okay, we all know how to factor this. We could say 2x, x. I suppose these both have to be 1s. I suppose they both have to be positive. Yep, pretty simple. Okay, now this cosine expression is going to factor the exact same way. Okay, if it's helpful to rewrite things in terms of x, factor, then replace it with cosines, you can do that. Or you can just factor it the way it is. I know I'm going to have a 2 cosine x and a regular cosine x, because 2 cosine x times cosine x can be that 2 cosine x squared. I know the only way to get the 1 is with a 1 and 1. Those both have to be positive. 1 times 1 is 1. And when I do the inner and outer kind of redistributing, 2 cosine x times 1 would be a 2 cosine x. We'd get a 1 cosine x for the inner. That would give me that same 3 cosine x there. Okay, so if you can factor this, which you've been doing since 9th grade at least, I'm going to say you can factor something like this. Okay, from there, same idea. The reason we're factoring is so we can split this into 2 separate equations and deal with them individually. So I've got 2 things to solve from here. We've got 2 cosine x plus 1 equals 0. And then cosine x plus 1 equals 0. Okay, let's solve these. First one, I'm going to subtract 1 from both sides, divide both sides by 2. That'll give me a cosine x is equal to negative 1/2. And just disclaimer quick, if you need to pause the video and work any of these steps out on your own, that's fine. Okay, let's go to our angles and standard position for that. Where will cosine be negative? Well, that's going to be where we have the negative adjacent side. So as in the second and third quadrants. So again, both those will have a negative adjacent side. Here my adjacent side's a 1. Hypotenuse would be 2's. Looks like root 3's will be the other side. Okay, so we're talking 60 degrees for our reference angles, meaning that my angle in standard position is going to be 60 short of 180, which is 120. And it's going to be a mess, but 60 past 180, which would be at 240 degrees. Suppose we can convert those. We'll say x equals, okay, I know 60 is pi over 3, so that 120 would be 2 pi over 3. And if we're pi over 3 past pi, that's going to be a 4 pi over 3 coming from that part. Okay, we'll put the answers together in a minute. Let's do our other factor then. I'm going to subtract 1 from both sides. We have a cosine x equals -1. Okay, I'm going to say it's easiest to solve that with a graph of the wave. Okay, when you're talking sines and cosines of 1, -1, 0. Okay, cosine goes like this. It runs between 1 and -1. It takes 2 pi units to complete a cycle. Therefore, the middle part where it hits that -1 will be a pi. All right, so we've got the pi there. Okay, solutions then. We'll say x is equal to, and here we want all solutions, the infinite solutions. So we'll say 2 pi over 3 plus 2k pi. Okay, adding that cycle to it. We'll say 4 pi over 3 plus 2k pi. And then with these graphs, you can do the exact same thing. We can just say pi plus 2k pi. Because if I added pi units to that, I'd get to another -1 point, and that would happen at 3 pi. Okay, so there's an example of factoring a trinomial problem. Hopefully you're seeing it's kind of the same idea as what we did with the other factoring problem, just a little bit different step to start off with. But once we get it factored, you solve the two parts the same way we did before. Okay, B's the same idea. Why don't you pause the video, work through that problem, and hit play to check your answer. All right, B, let's factor this guy, and I'm going to do it without switching to x's. Let's see here. If I want to multiply to a 2 sine squared x, well, there's one way to do that. 2 sine of x times the sine of x. Okay, if I want to multiply to a 1, there's only one way to do that, with a 1 and 1. And let's see here, I want to end up with a -1, so one of these has to be negative. I want a positive sign at the end. Okay, so that means that my 2 sine of x has to be multiplied by the positive 1 for the outer. And then the sine x times the -1. Okay, 2 sine x minus sine x will give me that sine x. All right, so there we go, we're factored. Let's set each of these factors equal to 0. 2 sine x minus 1 equals 0. That means that sine of x is equal to positive 1/2. Solve that with angles in standard position. All right, sine is positive in the top 2 quadrants. Okay, opposite over hypotenuse. Opposite side's 1, hypotenuse is 2. Adjacent side would be our √3, so we're talking 30 degrees again for reference angle. And same thing, 1, -√3, 2, 30 degrees. So my solutions to this part then would be 30, in other words, pi over 6. And pi over 6 short of pi, we could say 5 pi over 6. Okay, we'll hold on to those for a minute. All right, second factor, sine x plus 1 equals 0. Okay, again, here we're going to get sine x equals a -1. I'm going to go to our graph of the wave. That's going to go like this. I want to know where we hit the -1 at. Well, I know sine goes to 2 pi. Its middle point is pi. So 3 pi over 2 would be halfway between those. That's going to be where it hits that -1. All right, we can put all those together. X is equal to pi over 6, 5 pi over 6, and 3 pi over 2. I suppose we can say plus 2k pi for each of those. Okay, because we're looking for all solutions. All right, part C, I want to run through one special case of this type of problem. Okay, it actually makes life easier. We'll just show you what happens with this one. So we want to solve this, again, trinomial. Again, we'll factor. To get the sine squared, that's just going to be sine x times sine x. Okay, to get the 3, we'll have a 1 and a 3. And let's see here, that's got to be positive I need to get negative here, so I know it's got to be minus minus. Yep, I'd have a negative 3 sign and a negative 1 sign. That could be my negative 4 sign. Okay, there we go. So factors the same. Let's solve those factors then. Okay, here, first one we've got sine x minus 1 equals 0. So sine x equals, 1 is what we want to solve. I could use an eraser too, but there we go. We'll say that's a 1. Okay, so kind of like we just did, except for instead of the negative 1, we want this positive 1. Oh my goodness, I can't draw 1s. Which happens at a pi over 2. Okay, so I get pi over 2's first solution for this one. Okay, nothing new so far. Here's the one new part. Okay, sine x minus 3 equals 0. So I want to solve, where does sine x equal 3? Okay, hopefully after graphing this, that's kind of looking funny. Let's take a look at what we're looking at here. If I think graphically, I've got my sine function. I know it maxes out at 1. This equation is asking me, where does it hit? I suppose we'll go up a little bit more. 3. Well, it doesn't. Okay, it never gets up to 3. So we could say no solution for this part of the equation for this factor. Okay, that factor is a valid factor. It just doesn't give any solutions. It doesn't give me a way to make this equation equal to 0. Okay, so after all that, I still do have the one solution from the first factor. So there's a solution to the equation, just not the second factor. We'd say x is equal to pi over 2 plus 2k pi. And like I said earlier, going into a problem, you're not going to know how many solutions there's going to be. There could be 1 like in this case. There could be 4 like we saw. I think we've seen 3. There could be 2. Okay, it could be more if I want to be a jerk to you. But we'll leave it with 4. Okay, so there's an example of when you factor, one of the solutions doesn't give me anything, but I can still get a solution from the other factor. Alright, so that's it for section 5.2. So crank through the rest of the homework, give that factoring stuff a shot, and like always, if you're getting stuck, if you need help, make sure you're reaching out. We'll see you folks later.